we'll say 1.2 square centimeters. And L0, the gauge length, of 2.5 centimeters. Okay? So, instead of finding points on this graph, putting them in columns, calculating stress and strain, and then plotting stress and strain, this is what I could do instead. First, finding UTS. Look for max load. And divide by the original cross-sectional area. Because ultimate tensile strength is just the maximum stress, which is the maximum load over the area. All right. We can find the modulus . By identifying 2 points in the linear region. Load, let's see, it would be XY. So it would be delta X1, load 1, and delta X2, load 2. This axis, this x-axis, is not the length, but the change in length. Okay? So I have a bunch of different delta x values. So let's say I pick this point. And all that. No. I'll pick this point. So I'm going to say that that is 0.0025 in x and 500, 600, we'll say 580 newtons. And I'll say this point is 0.005 for the delta x and we'll say 1220 in newtons. Okay? And count, so then what I want is I need modulus, which is the change in stress over the change in strain. And the change in stress is the change in load over the original area divided by the change in extension divided by the original length. And that's the change in load over the change in delta x times L0 over A0. So I can do that, I can get those values. That's how I find modulus. And then the other thing we need is to find yield strength. That's a 0.2% offset. All right, and in order to do that, First, we need to determine what delta x is when the strain is equal to like 0, 0, 2. That's step 1. As when finding sigma y on the stress versus strain curve, draw a line parallel to the data that begins call this so that begins at delta x 0, 0, 2 and determine where this line crosses the original data. Call this load at field strength. Divide by the original cross-sectional area to get field strength. All right, so let's try this for the data that I've got. The maximum load looks like, and I'm just kind of eyeballing this, I'm going to say 50. I'll say that's 5,500 newtons. Now, here's a great chance to illustrate why we use significant digits. Would it be reasonable for me to say that the maximum load is at 5,541.37 newtons? Would that be reasonable? Well, it's possible, but can my eyes determine that? No. With that scale, my eyes are really probably not going to be able to go past the hundredths place in accuracy. And because of that, any number I generate using 5,500 is only as accurate as 2 significant digits. Okay? Even though the calculator might give us more, those other numbers are meaningless. And we know they're meaningless because I might get a number, well, let's proceed here. We have the original cross-sectional area as 1.2 centimeters. So UTS is equal to 5,500 newtons divided by 1.2 centimeters squared. And I have 10 to the second power of centimeters per meter, and I'm going to square that. So now I have newtons per square meters, which are Pascal. And I know that there are 10 to the 6 pascals per megapascal. And you could say, oh, that's times 10 to the 4 divided by 10 to the 6. I'm just going to divide my numbers by 100. And that's fine, as long as load is always given in newtons and area is given in square centimeters. If the area is given in square millimeters, that doesn't work. Okay, so you choose. If you can memorize the fact that if this is newtons per square centimeter, I'm just going to divide by 100. You can memorize that fact, or you can, just like I do, always write it out so that I make sure I don't miss it. So 5,500 divided by 1.2. 5,500 divided by 1.2 is 4,583 newtons per centimeter squared. Divided by 100, I get 45. I could say 0.83, but again, I'm only as accurate as the least accurate number here, least precise over here. So I'm going to say 46 megapascals. All right, any questions? Okay, second thing, determine, okay, so, there it is, E. I have two values of load and extension already. So I can say, change in load on 1220 minus 580 megapascals divided by 0.005 minus 0.0025 centimeters. Nope. Yeah, that's right. Wait, these are low, these are newtons. There we go. So that's 640 over 0.0025. So 256,000 Newton per centimeter. That's my value for delta P over the change in delta X. And I just need to multiply that by L0, which is 2.5 centimeters, divided by A0, which is 1.2 square centimeters. These centimeters cancel. And now I'm again at that newtons per centimeter squared. And so I can say I've got 10 to the 4 square centimeters per meter, and I've got 10 to the 6 Pascal per megapascal. And then I get 333 megapascals. And we typically express this in gigapascals, so 5.3 gigapascals. Any math errors there? Everybody see what I did? Anything look funny? I did not have to make 2 extra columns of data here so far, so that's great.
Would be meter squared in the bottom there.
Thank you. Yes. Okay, now finding yield strength might feel a little weird, but it's just not. First, we want to find out what is delta x, and strain is 0.002 or 0.2%. And so we know that strain is delta x over the original length. And we want to set that equal to 0.002. So delta x would be L0 times 0.002. And L0 is 2.5. So that's 0.005. So that's the value of extension when the strain is 0.002. And I'm looking for where is the strain equal to 0.002. If I took this graph and made my columns and converted it to a stress strain graph, I would be looking on the x-axis for where strain is 0.002, which would be the same place as where extension is 0.005. All right, so that's step A, find where that is. And then just like we did with our stress strain curve, we're going to draw a line parallel to the data line that starts where where the strain is 0.002, where delta x is such that the strain was 0.002. So that was here. So I just draw a line that's parallel to the beginning of this curve, knowing that the curve won't stay linear. So that looks like it's a load of about 3,600 newtons. Okay, so we drew the line. process data at load equal 3,600 newtons. So that means that the yield strength is that yield load of 3,600 newtons divided by the original cross-sectional area, 1.2 centimeters squared. That is 3,000 newtons per centimeter squared, which is equal to 30 megapascals. And some would say that would be faster than making pulling data, making two columns, plotting those, and then measuring our properties. The other way, the way I taught you before, has, well, let's see, how many places is there room for error? Lots. Estimating the values of load and extension so that I can put them in the column. There's always maybe some calculation risk in making those last two columns. Then again, plotting these, my eye, however good I am at that. And then estimating where the slope is. Whereas in this case, I still am making an estimation, but I'm doing it once. So probably it'll be more accurate. When you get tensile test question on the exam, you can do it either way, whichever you prefer. So I've passed out. Are there extra tensile tests? Perfect. So I passed out these, the set of data. This was, I had 1, 2, 3, 4, 5, 6 samples that I tested. And the only difference between them is how much carbon was in the steel. So there's a ASTM's protocol or standard for naming steels. And you'll see that each of these steels has 4 digits. The first 2 digits are 1 and 0. Steels that start with 1, 0 are steels that only have carbon. Nothing else is added to them to change their properties. The amount of carbon is determined by the last 2 digits in the 4-digit number. So there's a 1010, and then a 1020, and then a 1095, and so on. So a 1010 steel has 0.1 weight percent carbon. 1080 steel has 0.8 weight percent carbon. That's the only difference here. And these curves were, done the same way here, where I took the extensometer off way before I reached maximum load. But you can see the high point on the curve. All right, so 7, and there's 2, 4, 6, 8, 10, 12, 14, 16, 18, 19. Okay, so I'd like you to pair up, and there'll be a couple of groups of 3. And once you do elastic behavior, I am not breaking any bonds, I'm just stretching them and then letting them go back. So elastic behavior is only dependent on the bond strength. Now, the strength of a bond can change if I change the temperature. If I take a material and I heat it up, the bond gets weaker. That's part of the reason why things expand. But for a given temperature, for a given set of conditions, environmental conditions, I can't do anything to change modulus, because it's only a function of the strength of the bonds. And for steel, while we do have some carbon in the steel, it's way less than 1% carbon. It's not enough to affect the bond strength of iron. So the modulus of steel, doesn't matter what we do to the steel, for a given set of temperature and pressure application, the modulus is constant. It's only a function of the elastic behavior of the bonds. Now, anything that's a function of plastic behavior, that determines plastic behavior, now we're talking about breaking that bond, permanent deformation. And that we can affect with adding different things like carbon to steel, or deforming, or recrystallizing, which we'll talk about later. So one of the things that I wanted to sort of illustrate with this exercise is for you to see, I can do things to steel to make it stronger, but it does not change its modulus. All right? Another property that's only dependent on the bonds is the coefficient of expansion. Only a function of the bond strength. Can't change it by adding different things to the metal or to the whatever. Okay, so that's our illustration, our second example. Let's take a quick break. When we come back, I'll talk briefly about hardness, and we'll start talking about crystal structures and metals. So if that clock says 11:40, we'll start back at 11:50. And hardness is the same thing, but just at the surface. There are different scales for measuring hardness. Hardness is not a thing that you would measure in having units of stress or units of any units other than a number. All right, one of those scales there, I think, is probably the oldest, the Moore scale. And you see that the highest value is 10 for diamond, but that's not a linear scale there at all, right? Corundum is like a tool, high carbon tool, not steel, but almost ceramic. But you got quartz and topaz up there at the top. In the middle, fluorite, calcite, those are salts. Gypsum is a salt, and talc is the softest material. And when back in the day of doing hardness tests with those, you literally just start with a piece of talc, scratch your unknown. If your unknown is scratched, then it's softer than talc, which is impossible, but you get what I mean. You start the softest material and we continue to scratch until the material we're using scratches our test sample. And then we know that our material is harder than or softer than one of those minerals. But it's not terribly precise. To the left of that, there are two short scales, Rockwell C and Rockwell B. I'm going to talk about the Rockwell test. One of the disadvantages of the Rockwell test is that there are a number of different Rockwell scales, Rockwell A, Rockwell B, Rockwell C, Rockwell S, and they aren't linear with respect to one another. Some of them overlap, some of them don't. And then the far left is the scale called the Brinell scale. And the advantages of the Brinell scale is that it is continuous from softest to hardest, and it's linear, or reasonably so. All right? So the Brinell test is in a class called an absolute test. All of the other hardness tests, except for the Rockwell test, are absolute. All that means is we're applying one stress to the surface, and we're measuring the deformation that that one stress caused. Okay? The Rockwell test is a differential test. It applies two different stresses, and it measures the difference in deformation between the two, so it's more accurate. And it's called a differential test. So let me write that down. So hardness is the resistance to mechanical deformation at the surface. Hardness scales or hardness tests. There's the Bernal scale. It's an absolute test. So that means there's one stress is applied and one deformation is measured. And when you do that test, you have a very large, relatively large diameter steel ball, stainless steel ball. I think it's about 1.25 inches in diameter, with a reasonably high load, somewhere in the area of 500 to 1,000 pounds load. And you allow that indenter, that steel ball, come to rest on your sample. You don't let it impact, you just let it come to rest, and you wait some standard length of time. I think it's like 30 seconds. And then you lift the load or the stress off, and you use a micrometer to measure the diameter of the indentation. And you look up that diameter, and it'll give you a number, a Bernal number. Okay? So you measure, it's all manual. And the, we say BHN for Bernal hardness number. And the advantage of the Bernal hardness scale is it's one scale for all materials. All right, now the Rockwell scale is a differential. Test. You apply a minor load and measure the deformation. Then you apply major load and measure the deformation. And the Rockwell tester does the measuring for you. And it's really just measuring the depth of the indentation. And then it calculates based on the difference in those two depths. It gives you a number, a Rockwell number. Rockwell hardness as a function of the difference the Dale scale, the Rockwell scale. And the there are many Rockwell scales, each with a unique combination of indenter and major load. So for metals, most metals, the scale that you would use to measure the hardness is either Rockwell B or Rockwell C. High strength steels, Rockwell C, lower strength steels, Rockwell B. So Rockwell B is a 1/16 inch diameter steel ball and 100 kilograms major load. Rockwell C, for the hardest materials, is a diamond indenter and 150 kilograms. And you can see that there is some overlap between Rockwell B and Rockwell C. They're showing Rockwell B scale of going up to 110. The scale itself doesn't really go above 100. But sometimes you can use the tester to measure higher numbers, even though that's kind of out of its range of accuracy. Steels, high strength main plain carbon alloy steels, not tool steels, will have a hardness of sometimes as high as 65 Rockwell C. But those same steels that have been, say, annealed, not hot heat treated, they can have a hardness of Rockwell B of 70. And if you want to quantify how much harder you've made the steel, you can't really do it because those two scales don't overlap. So in lab, what we'll do is we'll take measurements with Rockwell B and Rockwell C, and we'll convert the values to Burnell so that we can compare apples to apples, essentially. So in the lab experiment we do, we'll do a lot of hardness testing on the Rockwell tester. As much of it is automated. Okay. So, I'm trying to read the time.
Yeah.
It's 1:57.
Oh, good. So let's start talking about crystal structures. So most metals have one of two crystal structures. looking, I don't want to erase it. So metals are crystalline, doesn't mean you can see through them. It means that the atoms in the metal have a repeatable arrangement through 3D space. And there's two crystal structures for most metals. Most metals haven't written that very well. Let's say one of two crystal structures for most metals. I'm going to give you a list of metals in each of them. So one of the crystal structures has gold, silver, and lead, and aluminum, and copper, and high temperature iron, and the other chromium and tungsten and low temperature steel and low temperature iron. So I think maybe you have enough experience with metals to be able to make some sweeping statement about the difference in these two crystal structures as far as properties go. Yeah? Is there some word that you could use to describe the difference between those two different groups of metals? Copper and lead are pretty soft, gold is quite soft, silver is pretty soft. Metals over here are soft. The metals over here are high strength, high hardness, soft, low strength. These have a crystal structure that's called face-centered cubic. And these have a crystal structure that's called body-centered cubic. And while there are a lot of different things that contribute to one group being soft and the other group being hard, one of the biggest reasons for that difference is these two different crystal structures. So what do these crystal structures look like? Well, they're both cubic. So that means that if we were able to look at a piece of one of these metals and look just at the atoms, we would see a sort of cube arrangement of atoms in 3D space. By cubic, I just mean that the smallest common denominator has the same length, height, width, and depth. Face-centered cubic, the arrangement of atoms that repeats in space has an atom at every corner. That's why it's called cubic. And an atom at the center of every face. Now, what I've drawn is what we might call an exploded view. so that you can see all the atoms. In fact, these atoms are all in tight together. And if I just looked at just this front face, only, what this would look like is that. And this is the face of the face-centered cubic. The atoms are not really touching, but the furthest orbit there is close, very close to the furthest orbit of the neighboring atom. So the face-centered cubic structure has one atom in each corner, one atom at the center of each face. What else can I say about it? Well, for all crystal structures, the dimension of the structure of the cell, the single structure, has a letter name. And since it's just cubic, it's the same in every direction. This dimension here is called A. And A is the lattice parameter. So in 3D space, this is also A, and this is also A. The lattice parameter A is the height, depth, and width of what's called the unit cell. If we could break down this repeatable arrangement to its smallest part or its smallest unit, it would be a unit cell like that, and that's repeating in 3D space. Face-centered cubic. So the other property, or the other thing to know about FCC is what is the relationship between the atomic radius and the size of that unit cell. And I can see that along this diagonal, those atoms are touching. And I know that's A, and that's A, so this length is the square root of A over 2. Sorry, A over the square root of 2. Right? A squared plus A squared. Nope, that's not right. It's just root 2A. A squared plus A squared plus H squared. A squared. Yeah. Don't know why that I just lost that. Root 2A is that length. And that's also equal to 1, 2, 3, 4 radii. So for face-centered cubic, 4 times the radius is equal to square root of 2 times A. So if we knew the radius, atomic radius, we would be able to know the size of one unit cell. If we knew how many atoms are in a unit cell and how much each atom weighs, then we could calculate the density of that unit cell, which we'll do next time. So how much does one unit cell weigh? Well, I've got 8 corners, and 1/8 of each of them is actually in the cube. So that's effectively 1 full atom based on just the corners. And then I've got face atoms, there's 6 faces, and 1/2 of each is in the cube. So 6 faces, and 1/2 is in the cube. So there are 4 atoms per unit cell. Right? So we know how big the cell is as a function of atomic radius, and we know how much each cell weighs as a function of how many atoms are in there. So we'll use all these things next time, but the equations the things that matter are just that there are 4 atoms per cell, and that 4R is equal to square root of 2 times A. This is soft materials, face-centered cubic. Body-centered cubic, 1 atom at each corner, just like face-centered cubic. Plus 1 in the very center. One at each corner. And 1 in the very center. So if I needed to know how many atoms are in the cell, I've got 8 corner atoms times 1/8. Plus 1 center atom. So for BC, I have 2 atoms per unit cell. Note that this BCC unit cell it's not exactly half as big as the FCC unit cell, but it's close to that. So it's not like they're all spread out in BCC and not in FCC. If I were to show where the atoms are touching, I would draw this plane. like that. That's what this plane is here. And this is A. But this dimension isn't A, it's root 2A. And the atoms are in contact along this line. One radius, 2 radii, 3 radii, 4 radii. Four radii is equal to the square root of 3 times A. So right now, what's important to know about these two different crystal structures is the different relationship between the radius and the lattice parameter and the number of atoms per cell. So the volume of a cell is what? A cubed, right? So that's equal to 4r over the square root of 3 cubed. All right, so if I know the radius of an atom, of a metal, the atomic radius, then I know the volume of 1 unit cell. And if I know how many atoms are in the unit cell, and I know the atomic weight, I know how much each cell weighs, I know the volume of each cell, so I could calculate the density of that material without ever having my hands on the material. So we're going to do that next time. Just a little preview. The density that you calculate, theoretically, is always bigger, not a lot, but a little bit bigger than the true density. The theoretical density is always a little bit bigger than the true density. And that's because of defects that we'll talk about. So volume of a ECC unit cell, 4r over root 3 cubed. The volume of an SC unit cell, 4r over root 2 cubed. Okay? And we'll pick up with that on Friday. No homework, but well, there will be some on Friday.